Hi. So this lecture is going to be on vector quantization and the relationship between vector quantization and autoregressive models like language models. So what is vector quantization and how is vector quantization related to language models? And this is going to be particularly important for modern multimodal models like GPT-4o. And this starts quite a while ago, about 8 years ago, with something called a VQVAE, a vector quantized variational autoencoder. And the basic thing that we're going to do is take an image, take a convolutional neural net, to take it up to some feature layer, right? So this would typically be somewhat smaller spatial dimensions, but have a vector at each position. And then what we're going to do is quantize these vectors. Vector quantization means you take a set of vectors and you you map each vector to a token, a symbol, like a language token. And then you give that token an embedding. That's one way to think about vector quantization. You're mapping vectors to tokens where the tokens have embeddings. And in something like k-means clustering, you're taking the embedding of a token represents a set of vectors, and each vector is going to its nearest token to represent it. I could give a lecture on k-means clustering, but that's what we're going to be talking about at a high level. So in 2019, so now this is 5 years ago, these are the first sort of class conditional image generation based on this VQVAE representation. And this was striking because up to this point, before this, GANs were producing good images, but VAEs were not producing nearly competitive images. And this was a breakthrough for VAEs, variational autoencoders, because it was producing images that were competitive with the GANs in that era. And this remains true today. These vector quantized, followed by language modeling methods, autoregressive image modeling is what it's called, remain competitive with diffusion models. It's another way of generating high quality images for arbitrary text prompts. So I want to go through in detail sort of how this works. So we're going to have a population of images. We're going to be training a convolutional encoder that maps those images to a feature array, an array of features. And then we're going to do vector quantization on these features to turn it into an array of tokens. Now, once it's an array of tokens, we've matched each vector to some token, something like you would do in k-means clustering. Now we've got an array of tokens, and we can language model that array. We can model that array using an autoregressive language model. That's what this represents. So in an autoregressive language model, you generate one token at a time using a transformer. So we're going to use we're going to generate these arrays of tokens, and we're going to model the array of tokens with a transformer. So this has two sort of independent steps. One is a VAE encoder that's mapping this image to an array of tokens, and the other is a transformer language model that's modeling the probability distribution over this array of tokens. And the fundamental thing about VAEs is, in principle, the prior and the generator can accommodate any encoder. So the fact that this encoder is trained without looking at the prior and letting the prior model it is, in principle, not a problem, because the VAE in principle can handle any encoder. It's not true in practice, and this encoder is going to have to be trained carefully to make this work. So just notation wise, we're going to take an image and we're going to map it to an array of vectors. And I'm writing Z encoder at position P for image Y. So P is a position, an XY coordinate position in this image. P is a position, Y is an image. And we've got a network that's producing a vector at that position for that image. So this is a vector in R to the D. And now what we're going to do is we're going to assume another data structure, which is a set of tokens. And each token is going to have an embedding. So this is just like a language model. In a language model, you have tokens, typically representing the words, but sometimes subunits of the words. Those tokens have embeddings, and then you can model a probability distribution over sequences or arrays of these tokens. So what we're going to do is we're going to assume a set of tokens. Each token is going to have an embedding. That embedding is going to be trained. That's going to be learned as part of our model. When I take this image and get an array of vectors, I'm simply going to map each vector to a token. So K encoder position is a token. And that's the token whose embedding is nearest to the vector that was computed. So I take this array of vectors, I map each vector to the token whose embedding is nearest to that vector. And that's this representation. That's similar to a k-means clustering of the tokens, except I'm assuming this is just the clustering part. I'm going to assume the token centers, the token embeddings are given, and I'm mapping each vector to its nearest token. So we now have an array of tokens. So the encoder and the decoder, this is the prior. We have an encoder that's producing the latent variable, which is this array of tokens. We have a decoder, which is constructing the image from the tokens, the token array. So I'm going to train the encoder and the embedding vectors and the decoder together, ignoring the prior. And this is actually sensible for a VAE. Okay, so now we can define a loss. We need to train this. We need to train both the encoder and the decoder and the token embeddings. So I'm going to take the probability. So when I take the decoding, right, I've got this array of tokens. I'm going to decode that into an image. When I decode that into an image, I'm not going to get exactly this image, but I'm going to get something that's near this image. And what I'm going to do is take an L2 loss, which corresponds to treating this decoder as producing a Gaussian distribution at each pixel. So I'm going to measure the squared error at each pixel. So this is measuring the squared error at each pixel between the actual input image and the decoding. So now I have an autoencoder, right? We're going to take this image and code it into an array of tokens, decode it back into the image, and now I'm going to use an L2 loss to define my reconstruction loss. So this is the reconstruction loss. It's just the L2 loss between the original image and the autoencoding version. No prior, just encode and decode. However, we've got a problem. These codes are discrete, which means that the gradient with respect to the encoder is 0 because the encoder is snapping to a discrete thing, and a tiny differential change in the encoder doesn't change the token array. So there's no gradient on the encoder. The encoder is not getting a gradient because we've got a discrete, it's producing a discrete value. And something that's producing a discrete value doesn't have a gradient. So what we're going to do is something called straight through gradients. So here's our reconstruction loss. And what I need is a gradient on the encoder. So what I need is to take the Z encoder. This is I'm writing this in sort of framework notation. This is a vector now, right? So this is the thing that takes the image to a vector before I tokenize it, before I quantize it. And what I need is to get a gradient on this vector. So I'm going to assume that this vector is near the encoding of the token. All right, if things are going well, when I snap to a token, I don't move much because I've got a vocabulary of tokens that let me find some nearby token. So I'm going to assume that this token, that the embedding of this token is near this vector. And that should mean that if I take the gradient of the reconstruction loss with respect to the embedding, that should be roughly the same as the gradient as if I didn't have the embedding, as if I was passing this straight through. So I take the gradient that I get on the reconstruction loss with respect to the embedding, and I apply it to updating the encoder. And that's called a straight through gradient. You're pretending that this quantization step didn't happen. And you're just taking the gradient that you get for the vector, the token embedding, and you're passing it back to the encoder. And that'll train the encoder. So we also want to get, we also want to train the token embeddings. We need to train the encoder and the token embeddings. So here's our reconstruction loss. So we've already said that this is the straight through gradient. Here's a k-means gradient. So the k-means gradient is going to say, I want the encoding, I want the embedding to be near the encoding. So this is going to train the embedding, right? It's going to, we're going to try to make the embedding, this objective function, if we hold the encoder constant, right? If we hold the encoder constant, if I train these embeddings to minimize the squared distance to the encoding, to an encoding that is snapping to this token, what will happen is this embedding will become the mean embedding of the tokens that go to it. So this is literally a k-means objective function. And it's a theorem that if you find a stationary point, if you run this training to a point where it's not changing, where all the gradients are zero, that the token embeddings will be the mean, the average of the embeddings that map to it. So this is taking the embedding. This is defining that way of training this embedding vector. And beta is just a way of weighting the various gradients on the embedding to adjust the relative learning rates. Sorry, that's going to adjust. This is just adjusting the relative learning rates of the embedding and the encoder. And now the decoder has a well-defined gradient with respect, because the decoder takes a token array and produces the image. And then finally, so we train that to completion with that objective. And finally, we take a transformer and develop a transformer language model of these image arrays. And this is, again, using a universality assumption, you can show that if you train the encoder and decoder together, such that you've got a perfect probability of image given latent, and then train the prior separately, under the universality assumption, it'll exactly model the population. So this methodology is associated with a theorem that says you're exactly modeling the population. Now, there's an interesting analogy to be made here, an interesting point, and that is when you tokenize. So in the original VAE model, the decoder did not tokenize, right? It just produced an image. But when you tokenize, you're choosing, you've got a set of possible discrete tokens that you can select when you're encoding the image. And that means that the encoder is basically drawing from a mixture of Gaussians. Each token is representing the center of a Gaussian distribution, or at least you can think of it that way. So by doing k-means on the vectors that are being produced, you're letting the model have a kind of mixture of Gaussian modeling component, which is a richer modeling component. So that's the point. This is talking about a normal Gaussian distribution, and with a k-means, you can think of this model as producing a center for each token in a mixture of Gaussian model. Okay, so this methodology is not limited to images. So this was used in a very well-known, impactful paper called Wave to Vec in June 2020. So this is 4 years ago. And what they did is they used this methodology to tokenize audio. So audio, like images, is continuous. And this methodology, the point of it is it converts a continuous input, like an image or sound, to tokens. And once it's tokens, you can use a language model, right? You can use a transformer to model sequences or arrays of tokens. So this methodology was applied to speech, to sound, to speech sounds. And by tokenizing the speech, and you can think of this tokenization as producing phonemes, automatically learning discrete representations, discrete phonetic symbols. They call them pseudo-text units. So you're transforming a sound wave into pseudo-text. Presumably you've got a much larger vocabulary of tokens than is typical in real linguistic phonetic analysis. What they showed is that this method of tokenizing speech, which is trained without any labeled speech, you're not labeling the waveforms. This is purely unsupervised sound waves. You're learning kind of phonetic tokenized representation just from listening to the sound. So this would be analogous to babies or young children learning the phonemes of their language just by listening to the sound. They sort of have to learn the phonemes before they can start hearing the words and attaching the semantics. So what they showed is that by learning these phonetic units automatically, just with an unsupervised way, that then when you train a language model, when you train a speech recognition system that works from the tokens rather than from the sound wave, you need far less training data. So they showed that with only 1 hour of human transcribed audio, they could reach the same performance, same word error rate performance as a state-of-the-art system that was trained on 100 hours. So you dramatically reduce the amount of training data needed. Okay, now if we jump to 2021, this was a big deal at the time. It looks silly now, only 3 years later. But this was a huge advance in image modeling. So here we're, for the first time, generating images in response to text. And we're doing it precisely by building a large corpus of text and images and modeling the conditional probability of the image given the text using this methodology. So we're representing all of the images as token sequences, and then we're using a transformer to take the text the transformer sees the text, and the transformer generates the token sequence, and then you get an image in response to the text. And this was shocking at the time. Not things have changed a lot in 3 years. So generative spoken language modeling. So this is about this is about treating sound waves as token sequences. Once you can convert a sound wave to a token sequence and you can model it with a transformer. So imagine taking sound waves, producing a token sequence, modeling it with a transformer. Now I can sample from that. And when I sample from that, I'm sampling sound. So I get a language model trained just on sound. And that model doesn't necessarily know the words, but it will speak. And doesn't understand the language as well as a real, GPT-4, some real language model. But it's shocking that you can train a language model just on sound, not on text, on sound, and it will generate sentences, intelligible speech with a reasonable amount of grammar. So I found that kind of shocking. It turns out that this approach, autoregressive image modeling, you tokenize the image, and then you use a transformer to represent the probability distribution over tokens, just like you would language. This approach, autoregressive image modeling, is competitive with diffusion models. So these are images generated, this is part T, images generated in this way, an autoregressive image generator based on tokenization of the images. Here's a more recent one, Chameleon. This is multimodal. So in GPT-4o is multimodal. And the simple way to do multimodal models is to take, you can take speech, you can take text, you can take images, you can take any kind of data and represent it as token sequences. And once you can represent it as token sequences, you can jointly model, say, text and images. You just have strings of tokens. Some of those tokens are image tokens. Some of those tokens are sound tokens. Some of those tokens can be actual language tokens. You can mix them all together and get something that it's multimodal, right? It can draw pictures. It can speak, do really high quality voice generation. It can generate text. So once you can get everything into token sequences, you have this nice uniform representation that can be completely multimodal. So that's sort of bringing us right to the cutting edge. And I'll end there. Thank you.